Thank you. Before beginning, I hope everyone's managing to survive here. The temperature, like in thermodynamics, we tend to generate more heat than light in our discussions, but the window is currently the widest I think we can get it. And the other one has been we've been thwarted in opening it so far. I opened that door, there's another one. So let's create more light than heat if possible. In any case, I want to talk to you about issues in the context of the relationship between thermodynamics and dynamics, or the microscopic world. There are very few talks in this meeting which use Monte Carlo methods. There's at least one. And if you're doing Monte Carlo, you know you've got a probability distribution and you pick things out of it. When we do molecular dynamics, people tend to think we're always at the molecular level and they pay lip service to the macroscopic. But these issues are very closely intertwined, and it pays us dividends to think a little bit about certain basic features of the relationship between dynamics and thermodynamics. Free energies are thermodynamic quantities, they're not microscopic quantities, yet we aspire to calculate them by using microscopic methods. Before I go any further, this is the sort of thing I'm liable to forget if I don't put it at the top of my talk, so I want to thank all the people who are listed in this slide, collaborators in a couple of companies, so I'll talk about some of the things we've been doing with them, and resources we use. Remember, I said at the beginning, we're in the business of high performance computing here. I can't do what I do now without access to resources at scale. Why? Because we want to do things in a hurry. Ultimately, we want to calculate things rapidly, accurately, precisely, and reproducibly, and the speed of which we do these things influences whether people pay any attention to us. At the sharp end of a clinical decision, I need to tell someone what action to take within hours or days. I have to have a method that's reliable, and then I'm in business, but I need scale at computing levels to do it. So quickly, that's what I'll talk about. I want to talk about the relationship between dynamical systems and ergodic theory, which is often used to justify how we compute properties at macroscopic level. So then the methods of binding for energy calculation, what we do to ensure they're reproducible, how we set these up so that they run in an automated way, so I can get answers in hours, not days or weeks. Okay, this is classical statistical mechanics. I don't have time to dwell on all the equations, they're standard. Most people write down Newton's equations of motion, which are the basis largely on which people solve molecular dynamics calculations. But I ask you to think of the probability distribution according to classical statistical mechanics. It's called ρ. It evolves according to the Liouville equation, and it has certain properties. You can make formal mathematical solutions of it using inverse Laplace transforms, but the main point I'm at here is, if I want an equilibrium state, I need to know the properties of this system at long times. If the system approaches a state that's independent of time, that's my definition of an equilibrium state. So the condition I need to have is, what does the dynamics need to fulfill such that the system approaches that state? And this is not new, but it's part of the subject of ergodic theory. And ergodic theory kind of parted company with people who do molecular dynamics 30 or 40 years ago. I don't often see these discussions in lectures or textbooks, but the requirement we need to get an equilibrium state is that the system is mixing in the hierarchy of dynamical systems theory. It doesn't need to be ergodic, and the next couple of slides will show you what the difference between a mixing system and a system that's only ergodic is, and there's a world of difference, but loosely, the system has to have these properties which make it unstable with respect to small changes in the initial conditions. This is at once profound. If I use philosophical language, it's of epistemological significance because it asks the question, what can I actually know of the behavior, even of a classical system that has thermodynamically interesting properties? And then what conditions I may need to draw from that, or consequences for doing these calculations. This is a pictorial representation, as it were, of the mathematics, and it simply says that I have some uncertainty in my initial condition that's always used in a molecular dynamics situation, then if this system is going to have an equilibrium state, oh, by the way, it will do because we're measuring free energies. Then those trajectories diverge exponentially fast, and there's an intrinsic property of the system, the Lyapunov exponent, that tells you how fast it moves. It sounds practical, of no deep significance, but I assure you it is, and this is one of the reasons why people have turned the subject of ergodic theory into a mathematical approach, because to explore the consequences of any assumption you make on the initial conditions, you need to understand the limitations of a computer. People tell you that the universe is a computer, and I say to you, yes, but all the numbers that you use in a computer, the IEEE set of floating point numbers, has zero measure with respect to all the numbers that exist, most of them being irrational. You understand that your initial condition can only be an approximation because you're using a computer. And that approximation has the consequences, but the picture of what I'm getting at is represented here. If the system is non-ergodic, it just goes round in a circle. That little hatchet is the initial condition, the set of initial conditions I start with. If it's ergodic, it will wander through all the states compatible with the energy. But if it's a mixing system, it does much more interesting things. Pictorially, it goes to the state where this probability distribution is uniform. So the question about the relevance of the ergodic theorem is moot here because it applies to those systems, but not necessarily usefully or as helpfully as it could to systems that are mixing. And you would have to run a very long time to get this to work, yet it seems to be used often as the way of calculating properties. So what happens if you do multiple simulations? This is quite generic, actually. This is taken from work we've been doing over many years with the 9 FDA-approved HIV-1 protease drugs. You run the same simulation n times. That's the distribution of results you get. The distribution isn't uniformly scattered. It's rather like a Gaussian distribution. The question of exactly what the statistics are is still open, because anyone who does statistical mechanics knows the interesting systems are ones that don't have Gaussian distributions, but these ones tend to. So we're just showing you what happens if you run the same simulation, in fact 50 times here. So this is the key to why reproducibility is such a problem when people publish results in molecular dynamics. One-off simulation doesn't have much value. I need to know much more about the system. And this is another picture taken from a recent paper based on a study of the peptide, complicated peptide. Epitopes are often called, bound to the major histocompatibility complex. And you will see what we did there to capture the statistics correctly. How long do you need to run the simulation? And as they say, read the paper to understand this, but 4 nanoseconds per run it 50 times, and you get the distribution, the ensemble distribution here. Run it for 1 microsecond, and you get that. So essentially, if you add up all the time you've taken, it's 4 times 50 nanoseconds is 200 nanoseconds versus a microsecond, and the results you get are much better. In fact, if you use 1 microsecond simulations here, you can't get a correlation with the binding affinity of the peptide with the MHC. You can if you use the right number of ensembles. So the problem often, characteristic in a character form, is hope to run single MB simulations and then hope then to get some correlation between free energy and the experiment. Of course, the experimentalists need to give us their errors, but it behoves us to produce errors as well. The situation we're in is one where we know one single simulation isn't enough. The other question is how many. And so from a statistical mechanical point of view, you could say, what's the number n of replicas I need, such that if I do one more, it doesn't change the result. And that's where we find what the numbers are that are necessary here. And typically, I'll just take you through what those numbers are, but if you do it nicely and it works out, you can get error bars of this sort. It's really similar to weather forecasting. The systems are different only in that we're solving Navier-Stokes equations, which are dissipative. In weather forecasting, here they're conservative dynamical systems. They still have the same chaotic properties. To know if it will rain tomorrow, we run ensembles of calculations with our Met Offices. That's what tells me with probability X it will rain tomorrow. So then, to get down to the sort of meat and drink of what people care about when they do these calculations, this is an example of the sort of thing we're interested in, using something like an MMPBSA technique, but trying to do it in a way where the results are obtained rapidly, accurately, if possible, precisely and reproducibly. And the main way of doing this as an endpoint method is to calculate one trajectory and assume there's no change when the molecule binds to the protein site. But if you want to relax that assumption and do 2 or 3 trajectory, then you have to do trajectories of the molecule in the solvent and the apoprotein as well. If you do all of those, and on a sizable computer you can then start asking what's the change, what we call the adaptation energy when the molecule sits inside the protein. You couldn't do that with one simulation. It's hardly ever mentioned in most of the literature, and the reason is because the fluctuations are so huge. If you only do one calculation, the cancellation, as they say, of errors is so huge here, you won't get anything but noise. But if you do it in the way I'm advocating, you can get good correlation. So this is, how much time do I have there?
10 minutes.
So this is the idea. Run a certain number of replicas, and there's no theory which would tell you how. It might depend to some extent on what your problem is. Here, for all the cases we studied, 25 is sufficient, but it's a dial. You can choose how big the error you'll have by cranking that up or turning it down. How long you run, so we can tell you what the error will be as a function of all these things. And it's much more efficient than trying to run these long simulations. It gives a reliable protocol, and then maybe this is aging, but when you find people reporting what happens when they did one simulation, in the light of the data we have, you can't take it seriously. But it's a function of computational power that we're capable of running so many simulations now. I keep saying 10 years or so ago, the largest computers might have only had a few hundred cores on them. Now they have hundreds of thousands. And whereas one was a heroic job previously, for some cases, it's utter chicken feed on a big computer. So then, how do you actually do these things in a hurry? That's related to computer science and sort of infrastructural issues, but we've invested quite a lot of time in developing something called a binding affinity calculator. It handles these type of calculations in an automated way, because you couldn't play this game if you tried to do all of these steps in a manual fashion. You build the replicas, you equilibrate them, you unleash production with your favorite molecular dynamics code. And by the way, I run the same code. It might be GROMAX on one platform, and I run the same code on another. I don't often get the same results because people change things, or even the same machine, there's some change in the software stack and things go wrong because of the instability of all this. But anyway, you can sort of see numbers here. How long does it take to do all the analysis? And it's a few hours, but I've used, let's say, of order 5,000 cores. And I get all of that done at once. And I can do it in an automated way. I think most people here are enjoy the subject of alchemy. Most people are talking about alchemical. That previous case wasn't, and it's interesting as it gives insights into a lot of information. That's why the endpoint are better, because we do waste a lot of time on these lambda calculations. It's good to try and minimize it. But I just want to tell you a little bit about our approach to those, because you see, thermodynamic integration succumbs to the same problem as these other things. They're molecular dynamics simulations. And this is just an example of what the rate of change of this V thing looks like with lambda when I run it a number of times. It contributes very heavily to the error in the calculation. But it's better to think of the molecular dynamics trajectory as something stochastic. It might sound hard because that's the challenge between determinism and free will. surely classical mechanics says exactly what's going to happen, but I'm telling you it can never tell me precisely for the reasons I spoke about earlier. It's like throwing a dart into a board. What you get is something like a stochastic distribution, the statistics are Gaussian. And therefore this process could be treated as a stochastic process. That integral is to be thought of as a Gaussian stochastic integral. Every point on it is a stochastic process with some mean and average. And actually from the theory of stochastic processes, I immediately know that the integral of a stochastic process is also a stochastic process, and it has a particular standard deviation associated with it. So there's a nice result. So that's how we do our thermodynamic integration, and it applies just as surely to all of these methods. The question for you is, how many times do you do this? Because these are dials and knobs, you can choose to control the errors. And that's the workflow, how it maps onto the supercomputer that I'm using. At a superficial level, this looks nothing but the same as the ESMAX thing. Those who are aficionados and love lambdas will see the difference, but we're just deploying all of them at once on the machine, and maybe for one calculation I need around 8,000 core hours, but I get the answer actually faster than I did for the other case, because there's less post-processing involved in this instance, and I have some error control. But you can use these methods with flexibility. We have designed a front end for this that enables us to deploy the application onto your infrastructure. It could be a local cluster, it could be a very large or set of high-performance computing resources, or it could be a cloud. So because time will run out, how much more have I got?
4 minutes.
This is just sort of looking at the types of systems we've analysed with these methods. So the MMPVSA thing in the ESMAX protocol is pretty versatile for many of the applications. There will always be issues here. Some of them are related to force fields, some of them are particularly challenging active sites with heavy metals, with charges on them and things, where people need to do better in terms of probably parameterizing. So, and there are different types of molecules. I mentioned using peptides, binding small molecules, and trying to rank them. I would say the ESMAX method is rapid, precise, and reproducible. It's not accurate, but it's pretty good at ranking, with error bars of the order of 1 kilocal per mole or so. In the ties case, you can crank those down to less than a kilocal. You can get them down to 0.5 kilocals per mole. You can drive them down to 0.25. I'm looking at Brad in the audience, who knows about how much money a pharma company might save as it gets more control on the errors of these calculations. But it's a question here of how much you're prepared to pay, computationally as it were, and in time to get the answers out. Time is running out of the proverbial sandglass. Just quickly taking a look here, a nod at Sarah Skerritt, who used to be at Pfizer, and it's in the audience in a collaboration we did there, which was run blind on their set of track A pain inhibitors in a project that they have subsequently published the experimental work on. Our challenge was to look at their set of compounds and make predictions of them, and then they revealed what the results were to us. The basic thing here is that people like the ESMAX method when it's done like this, precisely for the reason I gave earlier, that I get insights into this adaptation phenomenon. What's actually going on when the molecule goes into the active site? Is it a lock and key? Is it an induced fit? One or the other of that can give you insights into what step you might take next in a drug discovery context. And the story in this case is 3 trajectory is the best. There are instances for prediction where 1 trajectory works better, and that's because you're closer to a lock and key hypothesis. Ties for Pfizer, same sort of study here. For the cases where it's applicable, it works pretty well. And here's one in the but for the experimentalists. Many of the data sets we compare with don't carry even experimental errors on them, so it's hard to make a prediction where you have an error against an experiment which is a single point. So So I'm very keen on experimentalists also putting their errors in, because it helps us to see how robust our own methods are. In another study of bromodomains, this was with GSK, similar sort of story. We did the same thing and looked at how we would predict with the ties and the SMAX cases. And actually, again, the story there is similar for those molecules, that the adaptation free energies, when included, make the correlation better, and they provide insights for the experimentalists who are involved in the project in thinking about design. Ties here is even better, where it's working and applicable. And the last thing I wanted to talk about here is going back to what happens when someone tells you they've done a simulation and they've reported 1 or even 2 repeats. How do I know what the errors are on the calculation? This one is a bit like what some people advocate, which is an n equals 1 in the sense of one trajectory simulation, but then subjecting the thing to replica exchange. So you can do what we call ties, that methodology where we actually run a set of replicas at each lambda value and perform replica exchange at each of those lambda windows. You can see this is recent work that's just come in while we were preparing for this conference from Agastya in the front row there. What happens to the error as you increase the number of replicas, the number of times you do the whole thing, and it has a dramatic effect on that error bar. If you only do it once, the error bars are perhaps charitably of order a kilocal per mole. If you do it several times, it's of the order of 0.2 kilocals per mole. It's more expensive. Just imagine the Russian doll picture. We're doing alchemical. People don't like spending time doing all this computation between lambda equals 0 and lambda equals 1. We're doing it with a vengeance now. Replicas inside on the path and with replica exchange. But at increased expense, the error goes down in a systematic way. We can also drive it down by doing more replicas without doing replica exchange. So there would be problems if you pulled out the wrong higher temperature set. So the summary of my talk, drawing to a conclusion, is it's difficult to resist the reason why one should use ensembles in these calculations, because of the intrinsic instability of the dynamics of these systems. You can then try to do rapid, accurate, reliable, reproducible simulations, and the whole thing is intertwined. The fact that I do replicas gives me a handle on the error, and the fact that they're easily scalable outwards to large machines. Those machines are fatter now, they're not faster, the cores aren't getting any faster, there are just more of them. But since I can parallelize and scale out, I have an environment where I can compute till I'm blue in the face. We're lucky. We've just got an allocation on blue waters. This machine has 400,000 cores on it. It's replete with, those who love them, GPU accelerators, and about 128 million core hours to use in the next year or so. So we're not short of capability to run it here. So then you can start looking at these things in the context of prospective ligand design, and that's one of the areas we're particularly interested in. With that, I shall stop and thank you for your attention.